Welcome to Review 2A, which is more or less a review of Reading Assignment 4. The contents of the slides to follow are summarized here. Here I only want to go over the major issues, equations, and highlight the main points such as conventions and equations. There are enough worked out examples on the previous lectures, so we're not going to revisit those. All right, so the first thing we did was to look at basically the graphing of vector fields. So we introduced a methodology for sketching a field, but to make things easy, we restricted ourselves to 2D because at least you can visually see things. With 3D, the diagram would become a little bit too messy. We also found that we can use traces to sketch a 3D vector field on a particular plane if necessary. This is how vector fields derived from the application of the divergence or Stokes systems theorem were visualized. So we made very heavy use of traces when we were looking at applications of the divergence or Stokes theorem. The main point here when graphing was to identify the individual points, and so I had set up here a table. So for example, at a position say -1, 0, -1, 0 would basically put you at a point out here somewhere. So right here, -1, 0. At this location, what would the vector be? Well, the vector would essentially be, in this case, to take the x component and put it here, which would be -1, and the y component would be 0. That means the vector at this location would be 0, -1, which means it would be pointing downwards. And you could do that for a number of points. Chose to do basically -1, 0, 1, 1, 0, and 0, -1, which meant we picked a point here, a point here, a point here, and a point here. And what you can see very quickly is that you ended up with vectors that tended to form a closed circle. And in this case, the magnitude will change depending on how far out you are. So smaller as you get close to the origin, and longer, much larger magnitude as you get further out. So this is what we call a rotational field. Then we looked at line integrals, and so here the issue was to compute a tangent vector, and also we looked at normal vector. Normal only in the sense that if we were dealing with a 2D object, that is a contour in a plane, the normal had some meaning. If you were to look at a contour in 3D, then the normal to a contour can take on an infinite number of options. And so it's of no practical use. So only for 2D would the normal have practical use. So basically, we looked at two versions of computing the unit tangent vector to a contour. That's bold capital T. Parameterized and explicit representation. First step was always to determine the position vector that traces out the contour. This contour could be open or closed. And the bounds on T for parameterized representation was necessary, and the bounds on X for explicit representation. So what would this typically look like? Well, in 2D, we'd have some means of parameterizing the contour. In the case of parameterized, it would be X as a function T, Y as a function T. For 3D, there would just also be a Z component. For the explicit representation, X remains as is, but the Y component is a function of X. And if we had 3D, then the Z component is a function of X. In both cases, if we're trying to represent a line using a position vector, we need one variable. In this case, it's T. In this case, it's X. The next step is to compute the unit tangent vector, which is bold T, which is the derivative of R, the vector, divided by the magnitude of the derivative of the vector R. And that this vector is tangent to the contour. So the derivative of this is tangent to the contour. So let's go through these cases one after the other. In the parameterized case, R dot would just be components X dot, Y dot. And for 3D, there would be a Z dot term as well. For the explicit case, the derivative now would be with respect to X. So the first quantity would be 1, and the second would be just dy dx. If we looked at 3D, then there would also be a dz dx term. Okay, so the unit tangent vector then finally would be to take the vector and divide it by its magnitude. And so for the parameterized case, we would have this result, and for 2D and for 3D, we would have this. R dot magnitude would just be this expression here for 2D and this expression for 3D. For the explicit case, essentially go through the same process, the difference being here that the magnitude in this case would involve a dy dx for the 2D case and a dy dx and a dz by dx for the 3D case. All right, if you wanted to compute the unit vector normal to a contour using a parameterized or explicit representation of the contour, then basically we follow this procedure. A unit normal NS in 2D can point inwards or outwards from a contour. Similarly, as a tangent vector can be either pointing along the contour in one direction or in the opposite direction. The vector NS points outwards from a closed contour. This is a convention. That is, it points to your right if you traverse a closed contour in a counterclockwise direction. So this is something that sort of you keep in mind when we're talking about the normal to a contour. This was the convention we adopted. So in this case, we were able to show that the appropriate vector that represents the unit vector normal to the contour would have this form. And again, R dot would basically take on this form. And for the explicit case, it would take on this form. Again, just as a reminder that you can show that the vector NS is normal to the tangent vector by taking the dot product NS dot T and proving that the result is 0. You can use the results from the last slide and this slide basically just to convince yourself that the expressions that you see here are correct. Again, just recall that R hat or R with the arrow is a position vector. Okay, so now the question would be, we need the magnitude of the differential arc length vector ds for the parameterized and explicit representation of a contour. So again, recall this is a position vector in 2D, the position vector in 3D. This is where t is a parameterization variable and r is a position vector. In the explicit case, we would have in 2D x and y is a function x, and in 3D y of x and z of x. And x is the explicit variable. Again, r is a position vector. So the arc length vector ds would just be r dot dt, and the magnitude would just be the magnitude of r dot dt. Explicit, in the explicit case, this would be r dot dx. Again, this would be a function of x. You know, the x and y components would be a function of x, and the magnitude now would just be magnitude of r dot dx. All right, so if we now basically expand things out in detail, for the 2D contour, the magnitude of ds, for the case of a parameterized contour, would take on this form, and for 3D would take on this form. In the explicit case, we basically have a 2D contour. Magnitude of ds would take on this form, and the magnitude of the contour for 3D case would take on this form here. So these are handy expressions. Basically, you can refer back to when you actually have to do the specific calculations. All right, then we looked at surface integrals, and here all I've done is summarize the main points. So here, for instance, we would have in this column a position vector. Always start with position vectors. Then you have vectors defining the tangential plane. That's the plane that's tangent to the surface at a given point. And you would need two lines to define a tangent plane. And so that'd be two vectors. The unit vector NS is normal to the tangential plane and to the surface. ds would be the magnitude of the differential area, and the orientation vector at a given point on the surface. It's perpendicular to the surface would be ds is the unit vector, which is normal to the surface. That's n subscript s ds. So these are the things of relevance. Here we have a column for the parameterized representation of these entities, and on this column we have the explicit representation. Now, if we're trying to basically map out a surface, we need two variables. So here you'll notice uv for the parameterized representation. For the explicit representation, basically z would be a function of x and y. So you'd have two variables, in this case x and y, in this case u and v. So the vectors defining the tangential plane, well, you basically would take the derivative of this with respect to u, which would be one line, and derivative with respect to v be another line. So here are basically the two lines of particular interest. If we're dealing explicit representation case, then we would end up basically with the two lines which basically represent the tangential plane as being these two here. So T subscript U, T subscript V, T subscript X, and T subscript Y. The unit vector would just take on this form in the case of parameterized representation, and this form in the case of explicit representation. The magnitude will be just the magnitude of the differential area, which will be this form in the parameterized representation case, and this form in the case of explicit representation. The differential surface area vector, which is just NSDS, would basically be just taking these two and multiplying, and taking these two and multiplying. And so by multiplying these two, you can essentially see that the denominator term vanishes, and you're just left with TQ cross TV, du dv in this case, minus zx minus zy partial 1 dy dx. All right, so then we look at it in terms of, the types of calculations we would typically do. And there are two classes. One of them involved taking a scalar function and multiplying it by this differential area. And so this in the red is the case when we're dealing with a parameterized representation, and the green when we're dealing with explicit representation. The other possibility is to take the dot product between two vectors, which by definition in this case would be the flux that we're calculating. This would be the case if we're dealing with parameterized representation. This is a case for explicit representation. And so here basically the x, y's, and z's would have to be basically in terms of functions of u and v. Everything here would be in terms of u and v, and therefore the integration bounds would be in terms of u and v. Here, the integration bounds would be in terms of x and y, because this represents the explicit representation. All right, so just to note that the vector f in this case takes on this form, and I just basically show that when we say f, x, u, v, y, u, v, z, u, v, we just basically, when expanded out, mean this. And in the explicit case, when we expand this out, we mean this. Now, just to finish this slide, there are two options for NS. That is pointing upwards or pointing downwards. The problem statement or a convention will dictate which version to adopt. So, for instance, when we dealt with the divergence theorem, it was clear that the surface area vector would have to be pointing outwards from a closed surface. Okay, so here basically I just get summarized some important sort of formulas. So parameterized representation in 2D of scalar function, you could have something of this nature. If you write this in actual form, it would take on this form. And then finally, if you expand this out, this is what you're trying to calculate between an upper bound and a lower bound. If it's 3D, that means this would now basically be a function of three variables, but again, S. This would take on this form, and then finally, when you actually have to do the calculations, you'd be looking at something that looks like this. If you're doing explicit representation, then this integral now becomes a function of x, and y becomes a function of x. If you expand this out, then this is what you're trying to calculate in reality. In the 3D case, you just end up basically with a third term, z is a function of x, and you can see now that you also have a dz by dx term involved as well. So let's take an example for the 3D case here in terms of how this typically would be applied. Let's say that f of x, s, y, s, z is equals to 1, which means, and it has no units. Well, in that case, this expression would just become ds, okay? ds meaning that you're computing the length of the curve in units of meters. So effectively, if this is 1, it's this calculation that you're performing to compute the length of that contour in 3D. On the other hand, if this has units, so for example, kilograms per meter, then what are you actually doing? You're computing the mass of a curve, a mass of on a particular curve. And so the mass density at any given point on the curve is going to be given. And so this integration here would be in fact computing the total mass on the curve contour, and units of course would be kilograms. Okay, so now basically what about flux integrals? So here again is a quick summary. If we have a 2D vector field, then it would have a form looking like this. If we're dealing with a circulation integral in 2D, we can express the circulation integral in the following equivalent forms. We can have a parameterized representation, in which case would take on this form, and explicit representation would take on this form. Now, I made a note at the bottom here that circulation is normally associated with a closed contour. However, the units remain unchanged. So if we looked at this, we had defined anything involving a vector field dot product with a tangent vector. We said that was circulation. But in actual fact, most of the times when we apply this, it would be applied in the context of closed loop. So it's just something just to be aware of. Okay, so again, just to recall, this is what TDS represents in the parameterized form, and this is what TDS represents in the explicit form. All right, so the next thing is to do flux integral in 2D. The flux integral can be written in the following equivalent forms. F dot NSDS, this is the parameterized representation, and this is the explicit representation. Again, recall what NSDS from the previous slide. It has this form for parameterized representation and this form for the explicit representation. All right, for a 3D vector field, the only thing that's of merit is the circulation integral in 3D. And so not much has changed other than the fact now that the vector field basically it has a third component, which is the Z component. And so now basically the integral will look like this for the parameterized case and like this for the explicit case. In this slide, we're going to look just at a summary of the divergence and the curl of a vector field for the 2D and the 3D case. And so they're all in one common place. And so for the divergence, the basic definition we followed was to take a flux integral and divide by the area. And the flux in 2D would involve a contour. And the units are, for F, are flux per meter. Units of the divergence would be flux per meter squared. In the divergence, case of divergence, this would be the closed surface integration of the flux divided by the volume basically that's enclosed by that surface. And you let the volume go to 0. In this case, units of X are flux per meter squared, and units of divergence of flux of the field F is flux per meters cubed. In terms of the curl in 2D, we essentially just said it was a circulation integral divided by the area bounded by the contour, and then we let the area go to 0. Units for the field were circulation per meter, and then units of the curl of the field were circulation per meter squared. If we look at the curl in 3D, then there are 3 components to the curl, the X, Y, and Z component. So effectively, the same type of calculation, only difference is that you're dealing with contours on different planes, and you're dividing by the area associated with the on that plane. So for instance, if it was on the YZ plane, then the area vector would be pointing in the XZ direction. So if we were to write out the curl with all 3 components, then it would look like this for the 3D case. Units for F in this case would be circulation per meter, whereas the units for the curl of the field would be circulation per meter squared. If we look at the divergence operator in 2D, means we take the divergent, the gradient operation, dot product with the vector field. And so this partial operates on the first component, the second operates on the second component, and essentially they're added together. So this is the 2D version of the divergence of a field. In terms of a curl, if we're dealing with 2D, we can essentially replicate the 3D case by setting this up basically with the unit vectors in the first row, partial derivatives on the second row, and the function itself on the third row. Notice here that there is no Z component, and the function f and x can only be functions x and y. If we to compute the determinant of this, then this just gives you dg by dx minus df dy with an implied z hat direction. The divergence operator in 3D would now involve an additional term, dot product with the 3 components of the vector field, and you'd end up basically with the partial with respect to x, y, and z. In the case of the curl of an operator in 3D, we now basically would have components for the field for x, y, and z, and as a result, you'll have three components for the field, for the curl of a field: the x component, the y component, and the z component. All right, then we looked at a number of vector identities, and the two most important ones were what is the definition of a source-free field and what's the definition of a rotation-free field. So if we take the divergence and operate on the curl of a vector field, then that's equal to 0. On the other hand, if you take the curl of the gradient of some scalar potential, then that's equal to 0. And so we said that essentially that any irrotational field can be represented by a vector field which is related to grad psi, and any source-free field, we said, could be represented by a vector which had the form of del cross A, where this A we called a vector potential, and it had, of course, x, y, and z components. The last one here is just a scalar Laplacian. It was an example that we looked at because quite often you see the symbol. What does it mean? Well, this is effectively the operations that are performed to get to this final result. All right, so then we looked at the divergence theorem, and so all I've done is summarize the key points. What does it mean? What are the conventions? So the left-hand side and right-hand side of the divergence theorem are equivalent, and the direction of the area vector, which is basically a surface area vector, points outwards from the closed surface. That's the convention. So for example, if you had a problem statement as follows, that the vector field is some function of f, g, and h, that's the x, y, and z component, and you're given a closed surface, which is shown on your right. You have basically one surface, which is a hemisphere, and that hemisphere basically has a radius of a, of 2, and you have a base to the hemisphere, which is a disk of radius a in the xy plane, also a radius of 2. Then if you put the two surfaces together, then you have a closed surface that encloses a domain. And so, if we take this figure here and apply the divergence theorem, then this closed surface integral, which is a flux, would be equal to the flux of this lower surface and the flux of the hemispherical surface. That's shown here. The area vector here will be pointing upwards, and the area vector on this bottom planar circular segment will be pointing downwards, because by convention it has to be outwards from the surface. So this would be what we call the left-hand side. And the right-hand side would just essentially be to take the divergence of the vector field, which is a scalar function, and integrate over the volume enclosed by this exterior surface. Again, the divergence operator would basically provide you with this result, which is a scalar function. So these are the key points in terms of understanding what the divergence theorem is. Similarly, the Stokes theorem, we basically have to apply the right-hand rule. And so here the thing is to take the fingers of the right hand, and they point in the direction of the contour traversal, and the thumb points in the direction of the surface area vector on an open surface bounded by the contour. So for example, here, we'll come to this shortly, here for instance is your contour. The contour basically consists of 3 line segments, and the bounded area is the one that's shown in blue here. In this case, because we're going in this direction, you point your fingers in this direction, the area vector you assign would be pointing in this direction. However, the choice of area is not, is basically, can be anything you wish as long as it's the same boundary. So down below, I've shown the same contour, but I've shown this as a box which is pyramidal. So it's got a side face, another side face, and another side face. These all join together at this common boundary, which is the same boundary as you see here. In this case, the area vectors would be pointing upwards on the bottom surface, to your left on this side surface, and to your right on this side surface. So this would be the proper way of labeling when we're going to apply Stokes theorem. So for example, if we start with a problem that says to evaluate the integral, closed contour integral of f dot r dot t dt, this is nothing more than t ds, the tangent vector ds. And let's say the f had this particular form. C is a contour in red. It consists of 3 line segments that bound this plane. This plane is this blue thing that you see here. And the vertices of the triangles are given. Then the solution basically would be invoking Stokes theorem. Here's your closed contour integral. This is the actual way you would do the calculations involving parameterization if we're dealing with a parameterized curve rather than explicit curve. And this would be equivalent to the curl of f dot nds. And as I said, this nds can be any surface as long as it's a common contour. So you could basically have this as one possible surface, and these three sides as another possible surface. And so that's effectively what I've shown below here. You have the blue triangle, which would be basically S blue. And you have the gray. The area here would be, if you take the surface integral of curl f dot nds, this would represent the sum of three discrete surfaces. One here, and one here. So you can either do it this way, or you can basically just do it assuming the blue triangle. You just need to compute the curl. So the curl basically would take on this form. You're just taking the determinant of this to determine what the curl of the vector field is. So this is more or less, in a nutshell, how to apply the Stokes theorem. All right, having done the divergence theorem and Stokes theorem, we essentially looked at the 2D equivalent of the divergence theorem and Stokes theorem, and these were basically called Green's flux theorem and Green's circulation theorem, respectively. So all I've done is summarize the basic theorems. These would maybe have a 2D vector field. This would be the unit vector that's normal to a closed contour. This, of course, is a closed contour signal. And on the right-hand side, basically, we would have this expression here, and the vector field here is given on the right. For circulation, we would basically dealing with the tangent to the contour. In this case, we end up with this expression, and again, the vector field has the same form. And again, the TD is tangent to the closed contour as it traversed in a counterclockwise direction. The last thing we looked at was to apply the divergence in Stokes theorem when the region or field are problematic. And so I've shown here basically two pictures. This is basically vectors normal to a contour in 2D and normal to a surface in 3D. So you consider this as a trace if we're dealing with a 3D problem, and this basically just as a planar surface when we're dealing with a 2D problem. Similarly, here you can treat this as basically a contour if we're dealing with a 2D problem, but you can consider basically this as a, for the case of Stokes theorem, as a contour, and for a 3D problem, then this surface that you're dealing with here would not be planar, but potentially could be curved, which means these contours also would represent curved contours rather than on a plane. So these are the basic pictures that we make reference to. So for Green's flux theorem, basically, if we have problematic regions or problematic points, then effectively, taking this particular example, then Green's flux theorem would now take on this form. You'd basically be looking at three contours, one which would involve a contour that goes all the way around, one involving this, and one involving this. And so you end up basically with doing this contour integral, the minus C2 just means that we're going in the opposite direction than the contour that we both normally would consider as being counterclockwise. Similarly here, minus C3. Now you could also rewrite this as C2, in which case you put a minus sign here, as C3 here, and put a minus sign here. And so this would be equivalent to, say, applying Green's flux theorem to this object and to this object. So you'd end up basically a contribution for this and a contribution for this. But actually, when you add these two together, you end up basically with something that represents a whole area, excluding basically these regions where you've gone around the problematic points. So the only difference for this basically and the 3D case from the divergence theorem would be that these things now would represent surfaces as indicated, right? And so you'd have a lower surface, you would have an inner surface, and an outer surface. So in this case, basically, everything looks the same except n's get replaced by s's. So you'd have basically f dot ds1 plus, again, this would be in the opposite direction, minus s2, or you could write this as s2, and then you have a minus sign out front. Similarly here, you could write this as s3, in which case you put a minus sign out front here. And this would be equal to the divergence of the vector field over the volume. Volume meaning everything excluding the little region which you've isolated, which is hollow. For green circulation theorem, then you involve contours. And so in this case, you have these three contours. When you have basically looked at the total of the system as a whole, then these two contours would cancel, these two contours would cancel, and these two contours would cancel. And so you're left with closed contours for the inner, and the outer. And so that's why you see these three terms. On the right-hand side, basically, you would have the curl of the area, which is enclosed by this contour, and the curl vector field dot product of the area enclosed by this contour. So these are the two terms that you see here, and that was equal to, in total, the curl of vector field F dot NDS. So that was more or less basically everything in reading assignment 4. So that concludes review 2A. Thank you for listening.